In this episode, we're going to explore in detail what deep image compositing is. Now, this is divided into three parts. The first part is just to give you an idea of the scale of deep image compositing. In the second part, we're going to understand what deep image compositing is. And in the third part, we're going to look at the tools that Fusion has provided us for deep image compositing. So let's begin. Here I have three groups. One containing a deep image, one with deep pixels, and one is a normal Z-depth map. I have converted each of them into a 3D point cloud. So let's start with the Z-depth map. This is what a normal image looks like. We have foreground pillars, a sphere, a cube, and some background pillars. The foreground pillars and the background pillars have depth of field applied on them, and the sphere has motion blur on it, and a little bit of depth of field as well. So when we convert it into a point cloud, we can see that there are some missing samples or information behind the sphere and the cube. And we can also notice these edge aliasing artifacts near the pillar. These edge artifacts often occur in Z-depth map. And as we can see that whenever an object occludes a background object, the information behind that object is not rendered. Also, we know that the sphere has motion blur applied on it. So we should be able to see the red cube through the motion blur of the blue sphere. But in the point cloud data, all we see is a red patch where the motion blur is supposed to be. Now, this is an issue that is prevalent with Z-depth as well as the position pass. They don't handle transparency very well. In contrast, when we load the deep image, we get a much better result. Now, there is no missing information and the cube isn't bleeding onto the sphere. It also takes into account the motion blur and the depth of field effects. But that's not the only reason why deep image compositing is so versatile. Unlike traditional 2D images, we can move objects around using the DeepTransform node. For example, let's move this cube forward. Now it's on the same plane as the sphere. Let's look at it in the 2D viewport and we can see that this is what it looks like. Similarly, we can move the sphere behind these bars and it's rendering all of this in real time. We don't have to go back to a 3D software and re-render the scene every time we want to make some adjustments. We can manipulate the scale, size, position of any objects anytime in real time. Now, you might be thinking that's because I have rendered out each of these deep images separately. But even if I had rendered each of these deep images as a single image, I can still isolate each element and move them around while keeping their motion blur and depth of field intact. In comparison, using a position pass and loading it into the scene gives us similar results but with some glaring edge issues. And generally, we don't use 3D point clouds for anything other than a reference to place another 3D object. So for this, deep pixel compositing gets the job done in most cases. However, deep image compositing shines in very specific instances such as volumetric effects or fur or whenever transparency is involved. Now, let's have a look at what happens when I bring the sphere forward. Now, as you can see, the sphere appears to be coming through the bars, which is very useful for volumetric effects. We can see that it is keeping the alpha and the motion blur data intact. Now, I'll explain all of these in detail later on in the video, but this is why we use deep image compositing. Hi, I'm Shashwat. I hope you're having a really great day. Today we are going to explore a powerful tool in VFX called deep image compositing. And if you've ever been captivated by seamless or realistic VFX in movies, TV shows, or even games, and wondered, how did they do that? Well, deep image compositing is how they did it. But what exactly is deep image compositing? So to understand it, we first need to understand what is traditional image compositing. Now, traditional image compositing relies on 2D layers: foreground, midground, and background. They are stacked and blended using RGB and alpha channels. So while it's effective for simple scenes, traditional compositing struggles with complex elements where depth and overlapping are crucial, like smoke, glass, or motion blur. This is because traditional compositing has some major headaches. Overlapping transparent objects create layering artifacts and inaccuracies. Volumetric effects like smoke and fire are a nightmare, requiring complex holdout maths and often re-rendering for changes. And realistic motion blur with intersecting objects is extremely difficult to achieve in the traditional compositing. So, without deep data, artists must manually adjust layer order or re-render elements to fix the occlusion issues. Deep image compositing solves these problems by storing multiple RGBA and Z depth samples per pixel. This deep data is the key, as it allows each pixel to represent several semi-transparent elements at various depths, allowing elements to be composited based on their true 3D position, even if they weren't rendered together. Deep compositing accurately handles transparency by storing depth information for each transparent element. Volumetric effects are integrated seamlessly as deep data captures the density and depth of these phenomena. And motion blur becomes much more realistic with depth information, enabling accurate 3D warping. This is especially powerful for scenes involving complex phenomena like hair, smoke, fog, and detailed shadows or volumetrics. It also overcomes common Z-depth compositing issues such as edge artifacts or aliasing, and allows objects to be inserted or repositioned at precise depths without requiring a re-render. Additionally, deep compositing provides flexibility in post-production, as changes to depth and compositing can be made without re-rendering, saving significant time and resources. The result: cleaner integration, better control, and far more flexibility in visual effects pipeline. Back in the late 1990s, Pixar Animation Studios was revolutionizing animation with films like Toy Story. But rendering realistic shadows for complex elements like hair, fur, or smoke, that still posed a massive challenge. And traditional shadow maps, which just stored one depth value per pixel, it couldn't handle the job well. For example, let's take a ball covered in 50,000 hair strands. If we render it at 512 by 512, the shadow map looks grainy, while a 4K by 4K map gives us a cleaner result, but it ate up a lot of resources. So Pixar's Tom Lokovich and Eric Veach, in their 2000 SIGGRAPH paper, they introduced deep shadow maps, which is a game changer that stored multiple depth samples per pixel. This allowed compositors to realistically interact with semi-transparent objects, delivering stunning shadows without eating up much resources. They implemented this in RenderMan, which is their rendering software, using the dText format. So, deep shadow maps, they didn't just solve rendering. This sparked the idea of deep image compositing. So, by extending multiple samples to entire images, Pixar gave artists precise control over layered scenes, influencing blockbuster films like Planet of the Apes and Avatar and others, completely transforming modern VFX workflow. Now, this innovation rippled beyond just rendering into compositing. Deep image compositing took the principle of multi-sample depth and applied it to full scenes, letting artists tweak elements like motion blur or volumetrics with pinpoint accuracy. And later on, they were able to store this deep data in OpenEXtra, which allowed for a more integrated and faster production workflow. Since then, deep image compositing has become an integral part of compositing and VFX workflows. And in early 2025, Blackmagic Design had finally integrated this toolset in DaVinci Resolve and Fusion 20 version onwards. So previously, if we wanted a similar level of control, we would have to use a workaround using the deep pixel compositing toolset and expressions and Z-slices. But what exactly is the difference between Fusion's deep pixel compositing and deep image compositing? Now, let's quickly understand what deep pixel compositing is, how it works, and its limitations. And if you want to know more about deep pixel compositing in detail, I highly recommend you click on the link above or in the description box below to watch these two videos. So at the core of deep pixel compositing is the position pass. Now, what is a position pass? Position pass is a render pass that we render out from a 3D software that outputs X, Y, and Z channel as RGB 2D image. And using this position pass, we can create a volumetric effect such as fog. We can create volumetric holdout mattes to color grade or create special effects. And we can use the position pass to incorporate 3D elements in our compositing. DeepPixel also uses normal map, UV map, vector map, and others during compositing so that we can relight an object or a scene, retexture an object, or add normal or custom depth of field effects. But there are some limitations to it. Single sample per pixel. Only one set of data, position, color, or depth per pixel limits the ability to handle multiple depth layers, making it hard to composite semi-transparent elements like smoke or glass accurately. No true volumetric support. While it simulates fog, z-depth, or position pass, it can't represent continuous depth variation, resulting in a flat or unrealistic volumetric effect. And the alternative is to use Z-slices, which is a long and complex process, effective but time-consuming and resource-heavy. Weak occlusion handling. It struggled with complex overlaps, making it difficult to separate elements at different depths, leading to layering errors. Single depth value artifacts. A single Z value per pixel can cause edge artifacts or aliasing in depth-based effects like motion blur or depth of field. Complex workflow. It requires precise setup of multiple passes and tools, and misalignment or errors can cause compositing issues and require rework. Render quality dependent. And the quality of the result relies on clean, high-resolution passes, so noisy or low-resolution data can introduce artifacts requiring re-render or manual fixes. In contrast, deep image compositing is a more advanced technique, commonly supported in softwares like Nuke and now in Blackmagic Fusion. It uses deep image data where each sample stores multiple samples at different depths, where each samples include color or RGB, alpha or transparency, and depth, which is the distance from the camera. This multi-sample approach excels at compositing complex scenes, particularly those with semi-transparent objects or volumetric effects. So if we merge two or more of these images, we can be sure that they sit in correct position and depths. Now, let's go to Fusion. Okay, so here we are in Fusion, and over here I have this composition that I remade using DeepToImage tools. And these are some of the files that we are going to be working with. I have this image and this image. Now, they are both the same image, although this one is a bit darker, but they're technically both the same image. I could increase the color or the gamma, but I'll leave it as it is for now. Now, Fusion has provided us some controls for deep image compositing right in the onset when we load an image. And one of the ways we can identify which image is a deep image is if we go over here, we can see that this image is 1920 by 1080 float 32, while this image is 1920 by 1080 deep 32. So this image is deep image and this image is a normal 2D flat image. Now, another control that Fusion has provided us is if we go over to the inspector and in the format, over here in this first row, we see these two options, flat image and deep image. Now, these options are only available to us in images that have deep image data embedded inside each of these pixels. So if I click on this image and go to format, we can see that we don't have that option because this one is just a normal 2D image. Let's go back to the deep image, and over here what we can do is right now it's saying deep image, so that means we can do deep image compositing using deep image tools. But let's say I don't want to do deep image compositing, I just want to use this image as a normal 2D image, and hence all I have to do is if I go over here, I can press flat image and this is now a normal 2D image. And I know that because if I look over here, it now says 1920 by 1080 float 32. And if I select deep image, it goes back to being a deep image. Now Fusion has also provided us some deep image compositing tools or nodes, and we can have a look at them. If we go over to effects, we go to tools, and we go down here and select deep image, and these are the deep image tools that Fusion has provided us. Now the first tool that we're going to look at is the dRecolor node. Now this tool combines deep image data with an RGB multi-layer image. Now this has two inputs. One is the depth input where we connect our deep image, and the other is the color input where we connect our color image. Now to properly visualize deep data, since if it's a complex scene with a lot of elements and there's a lot happening in the scene, we might not be able to properly see the data. Hence, we will not be able to use it very well. Now we have this deep image, right? And we can see that it's quite dark. Hence, few of our details are lost in the scene. And to accurately see where each of these objects are without fumbling in the dark, we may use the color information of this color image and replace the color information inside this deep image. So, I'll just quickly show you what's doing here. So I have this dRecolor node over here. Now I'm going to connect the output of the deep image into the depth input of the dRecolor node. And then I'm going to connect the output of the color image into the color input of the dRecolor node. And look what happens when I load this dRecolor node into this viewport. Now we have replaced the original colors of the deep image with the new colors from this color image. And we can see that it still retains the deep image data. And we can do the same thing for this one. We can see that this deep image is a bit darker and this normal color image is a bit lighter. So let's replace the deep image with this color image, and we're going to copy this dRecolor node. We're going to connect the deep into the deep input, and we're going to connect the color into the color input. Let's load that into the viewer over here, and we have replaced the deep RGB with the normal RGB and still retained the deep image data. Now there are some controls over here in the dRecolor node. The center X and Y basically repositions the 2D RGB image over the deep image. And the target input alpha is, well, we use this to enable the alpha channel from the color image in case we need to influence the transparency pixels in the deep data. And the drop input 0 alpha, well, when this is enabled, pixels in the RGBA source with 0 alpha are ignored and they won't influence the deep image. Now, the next node that we're going to look at is the dMerge node. But before we look at the dMerge node, let's understand what the normal traditional 2D merge node is doing. So let's load a merge node over here, and let's just copy this and this one over here. And let's see what's happening. Now, a normal merge node only has two inputs, a background input and a foreground input. And it mixes and merges these two images, these two inputs, using alpha channels and apply modes or blend modes. Now, let's have a look at what it looks like if I merge these two together. So this is our background image. This is our Puddu image. And let's connect the background image into the background input and let's connect the foreground input into the foreground. Let's load that into the viewer, and we can see that our scene has been merged nicely. But if let's go back to frame number 20. But if you look over here, we can see that our ladybird is, coming in front of the tree, whereas in fact it should be behind this tree. Now, why is that happening? That's because the normal merge node is basically just slapping the foreground image on top of the background image. And so if we want to move the ladybird behind this tree, we would have to create some complex holdout mask, which would become even more difficult for us to control and animate if our camera was being animated as well. Now this is where the dMerge node shines, because it's not looking at the foreground input or the background input. It is in fact looking at the deep information that is being stored inside each of these tiny little pixels. And so when it merges these two or more images, it places those pixels exactly where they are supposed to be. So let's load the dMerge node. Now there are a few ways we can go about loading a dMerge node. If we go to Effects, we can go to Image and load the dMerge node from there. Or we can right click in the nodes area, go to Add Tools, dPimage, and we can load the dMerge node from there. Or we can press Shift Space and type dMG, shortcut for dMerge, and load it from there. Or a more faster way to do is, let's click on the output of this dRecolor node, drag it and drop it on the output of this dRecolor node, and it automatically connects these two using a dMerge node. And if I load it into the viewer, we can see that our ladybird is now automatically behind this tree. So even if I move the frame to frame number 10, we can see it's behind over here. And if we go over to frame number 40, we can see that now it's over here, and slowly it's going to come into the foreground and sit on top of this book. And the dMerge node, unlike a normal 2D merge node or even a 3D merge node, does not have any controls. We can see over here we have many controls over here, and if I load a 3D merge node, we can see that we have some controls over here as well. In the transform, we can move the merged objects around and place them wherever needed. We can group these 3D objects together. But we don't have any control in the dMerge node. That's because it doesn't need any. The only job of a dMerge node is to merge two or more images that has deep information and position them exactly where they're supposed to be by reading the depth information that is embedded inside each of these pixels in each of these images. Now, the next node that we're going to look at is the DeepToPoints node. And I've showed a similar technique in the previous tutorial on deep pixel compositing. This is very simple to use, as here we don't even need to write expressions or invert the position pass and then use particles and spread them as point cloud using the position pass and expressions. No, here we bypass all of that. So let's go over to Effects. We're going to select the DeepToPoints node, drag and drop it into the viewer, and we're going to hide the effects. Now, what the DeepToPoints node does, it looks at the deep image, and when we connect this, it's going to convert this 2D deep image into a 3D point cloud. So let's quickly have a look. Let's connect the dMerge node into the DeepToPoints node. Let's load it into the viewer. And we can see that our 2D image is now become a 3D point cloud, although it still looks a little bit flat. So let's see what we can do about it. Now over here in the inspector window of the DeepToPoints node, we have these two options, scale and depth scale. Now the scale is the regular scale. We can scale this deep image in the X and Y axis uniformly. And the next option we have is the depth scale. That means that we can scale this image in the Z axis. So now we have spread this point cloud data in the Z axis. Now the depth scale is okay for a quick work because it's just spreading them back in the Z axis and it's not going to give you the proper depth and dimension of the original deep image. And for that, what the DeepToPoints node need is a 3D camera. So we can use a Fusion's 3D camera, or you can load in the 3D camera that you use to render out this scene, which in this case, this is an Alembic 3D camera. And I'm going to connect this 3D camera into the camera input of the DeepToPoints node. And the moment we do so, we can see that our 3D point cloud data is now spread out uniformly in our scene with the correct perspective and the correct scaling. Now if we try and add a 3D object into our scene, it's going to sit properly and have the correct dimensions. Now let's look at some of the controls of the DeepToPoints node. So over down here, the moment we connected our camera into the DeepToPoints node, our scale and depth scale parameters are gone, replaced with this default camera, which basically means if you have multiple cameras in our scene, then you will have to basically choose which camera you want to use, in which case I want to use just this one. Now going back to the top, we have these two options, a cross and a point. Now these styles is basically just for visual representation. For example, right now what we are seeing are these very small points. But if we don't want to look at points, we can select cross and look at the scene with crosses. And we can change the size of these crosses as well using the size slider. Or if we want to, scale it non-uniformly, then all we have to do is switch off lock XYZ and we can scale it non-uniformly in the scene. And if we go to the points, it changes back to a uniform size slider. Down here we have the density slider. Now the density slider is exactly as its name implies. If we increase the slider, then we are adding particles to the scene. There we go. We can see we have added more particles to the scene. But if we reduce the density slider, we can reduce the number of particles that are visible in the scene. Below the density slider, we have the default color where we can change the color of these particles. Right now, we have the use per point colors checked on, which basically telling Fusion to use the colors that were naturally embedded inside the deep image data, which is these colors. But if we switch it off, we see this white color, which is default color. And we can change the color of this scene into any color that we want, whether RGB or any color in between. Now the way we can use this is as such. Suppose we have 2 or more point clouds in a scene and we are not able to see them properly, see each of these object properly because of the per point color. So what we can do is we have these two images, which is the background of this ladybird deep image. And so let's just quickly convert these images into DeepToPoints. So I'm going to move the camera on this side and we already have this. And let's remove the merge node and move it over to this side. We're going to copy this. We're going to connect that. We're going to connect this to the camera and we're going to connect them using a merge 3D node because this is happening in the 3D viewport. And now let's load it into the viewer. And let's go to this ladybird DeepToPoints node and we're going to switch this off and let's change its color to red. And let's go to the background DeepToPoints node. We're going to switch use per point colors and we're going to change its color to blue. And now we can very easily see where our ladybird is. We can see that it's over there. So this is how we can use the DeepToPoints node in case we have multiple deep point cloud data for each of our objects. Now down here we have an option called Make Renderable. Now what Make Renderable does is it makes these point clouds visible in the render 3D mode, as well as it makes these point cloud solid enough that we can interact with them. For example, first let's load a render 3D node. We're going to connect the DeepToPoints node into the render 3D node and let's split the screen and we're going to load this over here. Now immediately we can see that we can't exactly see anything at all in the render 3D node. But the moment I select Make Renderable, we can see that now our scene is now visible in our render 3D node. In fact, let's just increase the density. And now we can clearly see the 3D point cloud in the Render 3D node. Now let's load a Shape 3D node, and we're going to merge the Shape 3D right in between over there. Let's load this into the viewport over there, and let's change the shape to sphere. Now, what Make Renderable also does is make this point cloud interactable with a 3D object. First, I'm going to switch off Make Renderable. I'm going to the Shape 3D node. I'm going to add a 3D Transform node. And if I use the translation picker and try to place it somewhere over there besides these candles, well, we can see that we are unable to do so. But the moment I make it renderable, and now if I use the picker and place it somewhere, we can see that it works. And we can see it in our scene as well. Now another control, the last control that we have just below Make Renderable, is called Unseen by Camera. So now we have a 3D object in our scene, and we have placed it with the help of the 3D point cloud data that we have created using the DeepToPoints node. Now we can just remove this, but let's say we want to use it to place another object in the future, and actually we just don't want this point cloud to be seen in the Render 3D node. So if I click on Unseen by Camera, what that does is it removes the point cloud data from our Render 3D node while it is still visible over here, and it is still interactable with the scene. Now over here, I actually don't like this candle flame, so I want to replace this candle flame with a real life candle flame, right? So I have a candle flame over here that I got from Pixar. Let's bring it over there. So this is the candle flame that I have, and I'm going to replace this candle flame with this one. So what I'm going to do now is I'm going to convert this candle flame first into a 3D image. So using the image plane 3D, I've converted this candle flame into a 3D image, and I'm going to replace this candle flame with this one. So let's connect this after the merge, after the DeepToPoints node, using a merge 3D node. Let's load the merge 3D node over here, and let's go to the DeepToPoints node, and I have all of these active, and you can see real time what's happening over here. Let's quickly add a 3D transform node, and let's zoom in over here, and let's quickly use the picker to place it over there, and then we can just manually adjust it however we want. There you go. And let's also switch that off, and we're going to scale this manually. There we go. So we have placed a candle flame in our scene, and let's look at it from the top angle, and let's rotate the candle flame to face towards the camera, something like that. Okay, and now I'm just going to do the same thing for this candle flame, for this candle flame, and for this candle flame, and I'm going to fast forward this entire segment. Now we have created these candles, and I've rendered each of these candles out separately, and I'll tell you why in a moment. But first, let's just have a look at what's happening in the Render 3D node. Now, over here in the Render 3D node, what we can do is we can either render this candle flame out as a normal 2D image, or we can render this out as a deep image. Over here in the output type, we have an image which is normal 2D image, and we have the deep image to render it out as a deep image. The render type, when we're rendering out deep image, I think it's better to select a hardware renderer. In the maximum texture depth, we should select float 32, and in the image, we should change the depth from default to float 32 as well. And let's load that into the viewer, and we can see that we have a deep image in the scene. And I'm just going to replace these three with this. So I'm going to Control C and press Shift B to create an instance. Once more, and I'm going to delete these, move them back, and connect that so that they're all deep images. And I can now merge them using the dMerge node. There we go. And I can merge this back with our original scene using the dMerge node. So let's copy this, paste that, let's connect that. And we're going to drag this output, drag it over there, use this. So we have merged this output over there, and let's load that into the viewer. And now we have candles in our scene, and they're sitting in the correct position. Deep image compositing is actually a very versatile tool. There are many things we can do with this, and one of those things is that we can convert a normal 2D image into a deep image. I have this woodland scene, and I want to replace this background behind this window with this woodland scene. So first thing that I would have to do is to convert this image into a deep image, and I do this using the ImageToDeep node. So let's go to Effects and drag the ImageToDeep node into the nodes editor. We're going to connect the woodland scene into ImageToDeep, and if I load it into the viewer, we can see that this is now a deep image. This is what it looked like before. So this is what our scene looks like, 4500 by 3000 integer 8. But the moment I connect it to the ImageToDeep node, it says 4500 by 3000 deep 32. So we have converted this normal 2D image into a deep image. Now let's look at some of the controls that we have in ImageToDeep. So we have this specify Z checkbox, and we can use this to specify the current Z depth, and if it's unchecked, we can adjust it using the Z scale and the Z offset sliders. Z scale allows us to scale this image in the Z axis, while Z offset allows us to move this image in the Z axis. And I can show you an example. If I merge these two together, let's load that, and if I go to ImageToDeep and I say move the Z offset, I can move it in the scene. So that's what it does. We can also position it in the scene using the center X and Y. So now we have converted this image into a deep image, but we can see that the resolution of this image does not match the resolution of our original scene. So we would have to reduce the resolution of this background of this image to that of our original scene, and we do so using the dResize node. Now dResize node is just like any other resize node in Fusion. It just resizes one image into the resolution that has been set in the inspector window, which is 1920 by 1080. And if we look over here, it says 4500 by 3000. And the moment I load the deep Resize node, it is now showing 1920 by 1080. Now, this is just an example. In real case use, some elements of a scene may have been rendered at a different resolution for whatever reason. Or you are using an image or a video of, let's say, a smoke, which is of a different resolution compared to your original scene. So in that case, you may need to use the deep Resize node so that everything fits well in the scene, which in this case is 1920 by 1080. Now the next node that we're going to look at is the dCrop node. So over here we can see this window and this background behind the window, and we need to remove this. So if I load DeepToPoints node over here, and you can see that this is the background that we want to remove behind the window, and we do this using the dCrop node. So drag and drop the dCrop node, and we're going to connect this over there. Now what the dCrop node does is, using this slider, I can either crop the deep samples from the front or from the back. So if I use minimum Z and move the slider, you can see that the scene is being cropped from the front. Similarly, I can crop the scene from behind as well. Now this is a good tool to clear out undesirable deep samples from the scene, which is this one over there. So I'm going to use the maximum and bring it down just a little bit, say 15, maybe a little bit more, and let's see if we don't accidentally crop anything. Okay, so it's somewhere between 10 and 7. So let's see, let's try making it 9. We have just a tiny amount of this sample over there, and so let's try and making it 8. There we go. So you've cropped out this undesirable background sample, and I'm going to connect this now over there, and let's load that into the viewer. And we have now a scene with this undesirable background removed. And now I can connect this woodland background over there, and I'll do that. First I'll just connect it using the merge node, and we can see that it's just right straight in front of us. So what I can do now is I can move this backwards using a DeepTransform node. Now let's first quickly look at some of the settings of the DeepTransform node. Now this segment over here is exactly similar to our normal 2D transform node. We have X and Y, so which means we can move our image in X and Y. We have pivot, which basically means we can move the pivot X and Y. We have size, we can scale it uniformly in relation to the pivot. So if I reset that, we can scale it over there, or we can say switch that off and scale it in the X and Y like so. But the way it differs from a normal 2D transform node is this scale Z and translate Z. Scale Z scales a deep image in the Z axis, and translate Z moves a deep image in the Z axis. So we have now moved this image behind the window, and if I add a DeepToPoints node after this, let's load that over there, and let's add a camera. We can see that we have moved our image in the z-axis. If I reset this, right now it's right in front of the camera lens. But if I say 5, we can see that our image is now over here. In fact, if I just bring it back forward just a little bit. So what we have done is we have separated this entire background from the foreground, which is this part, and it still works. But I want the woodland to be behind the window, and if I move this, if I say translate Z9, there we have it. Our image is behind the window. And let's also reduce size of the scene just a tiny bit. I'll switch on the uniform scaling and just reduce it a tiny amount, and move it in the y-axis to fill that area. There we go. And we can see real time how it looks like here in the 3D viewport. So this is the DeepTransform node. Now the next tool that we're going to look at is the dHoldout node. Now this is one of the most important nodes in DeepToImage toolkit. Compositing using deep data is heavy on the machines. Even powerful machines will slow down to process all of that data. So most of the time, why we render out deep images is to extract dynamic holdout mattes to continue the work using traditional 2D compositing, making the job faster and easier. So what the holdout node does is it creates a holdout matte using the foreground deep image to occlude background deep image samples, either by removing them or computing the value after occlusion. Let's have a look over here with this scene. I want to separate the background that we just created from the foreground elements, which is the entire house. But I want to keep these pockets where the branches and the leaves are supposed to be. I want that to be included. So what we can do, instead of using a merge node, I'm going to use the dHoldout node. This background node is our background image. So let's connect this into the background input, and we want this to be occluded by these. So I'm going to connect these to the foreground input, and when I load this scene over here, we can see that it has now dynamically occluded our image. Now if we merge these two together over here and zoom in, we can see we have these very weird edge artifacts. Now if we get these artifacts, let's go to the dHoldout node, and we're going to say compute occluded samples, and it's going to look at the transparent samples in this deep image and use that to correctly occlude our image. We can also move this holdout matte dynamically in the 3D space or in the deep space using the holdout Z offset as well as the holdout center X and Y. Let's have a look at holdout center X and Y. So if I move this over there in the X axis, we can move our holdout matte in the X and the Y. And if we want, we can move this holdout matte in the Z space. There we go. Let me show this with another example. Okay, so let's go over here, and we have our ladybird and our background. Let's create a dHoldout node for this. dHoldout, and let's connect this into the background, and we're going to connect this into the foreground, and let's load this over here. And what we have done is we have pulled out the ladybird from the background, and if we go over to the holdout center X and Y, we can move this holdout matte around in the scene, and we can also move this ladybird holdout matte in the Z offset. Now we've moved this holdout mat behind the table. Let's make it 5. And let's just bring it up. And now our ladybird holdout is just in between, like coming out from in between the table. And we can find a way to use this creatively. Now, before we move forward, I'm just going to quickly create some dynamic holdout mats for each of these elements. So I'll come back once I've created it. So here we have all of these deep holdout nodes. And this is how we created these. And let me also explain this complicated mess over here. So this is an industry standard technique, often used in big projects and big compositing, where there are lots and lots of elements and we want to create holdouts for each of them. So this is the technique that is used. I'll also quickly explain how we use this technique. So over here I have this background image, this ladybird image, and this woodland image that we just created. And these are all deep images. So now what we're going to do is we want to create a holdout for each of them. First, let's create a holdout for the woodland. So what we are going to do now is we are going to merge these two together and then use this merge node as the foreground input for the deep holdout node. So let's add a merge node and a deep holdout node. And first, let's merge these two images together. So we have this and we have this holdout node over here. So we're going to connect the deep merge into the foreground input of the holdout node, and we're going to connect our woodland image into the background image of the holdout node. And if I load, this is what it looks like. Let's organize it like so. Now we're going to do the same thing for this ladybird image. So I'm going to copy this, paste it, and this time we're going to merge the woodland image and this background image. And we are going to connect our ladybird image into the deep holdout node. Let's load it. This is what it looks like, and we can see it's being masked out nicely. Finally, we're going to do the same thing for the background image. So let's copy this once more. And this time we're going to merge these two together and then connect this background image into the background input of the deep holdout node. And if I load this, this is what we get. And this is the wing of our ladybird. And if I just bring it few more frames forward, we can see our holdout mat. So this is the technique that I have used over here, and this is the technique that the industry uses in case of big projects with multiple elements. Now that we have our deep holdout images, the last tool that we are now going to look at is the DeepToImage node. Now, once we have these mats, what we can do next is to convert these holdout mats into 2D images. Basically, we are removing the deep information that is stored inside of them to use these mats or images for traditional 2D compositing. So go to Effects, go to Deep Image, and up here we see DeepToImage node. Let's drag and drop it over here. Now I'm going to connect this Holdout node to DeepToImage node and drag it over here. And we can see that we have converted this Holdout node or this deep image into a normal 2D image. Now let's do the same thing for the rest of them. So Control C, paste. And now let's look at this one. This is deep. Now it's a normal 2D image. This is a deep image. Now it's a normal 2D image. Same. 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 And same. Now I can use this to continue to do normal 2D image compositing. For example, I can combine all of these images using a multi-merge node. So over here, if we look at this image, as I said earlier, let's assume we want to change this candle light to emit blue light. Then all I have to do now is, after this DeepToImage node, I'm going to add a color corrector node and I'm going to change the color to blue. Let's load that. So we need to change the color to blue. And now let's say I want to give it a glow. So after this, I'm going to add a soft glow. And again a soft glow, and this is what it looks like in the scene. And let's increase the gain. And we can see that it's basically the soft glow is being added on top of this entire layer. And I want the soft glow to be behind these branches. So what I'm going to do now is I'm going to add a bitmap node. And I'm going to connect the DeepToImage node to the bitmap node. Let's load it over here. This is our bitmap. And I'm going to connect the output of the bitmap into the glow mask of the soft glow node. Now it's only going to use these areas for glowing, and I'm going to give us a better glow. And also in the soft glow node, I'm going to switch off the red and green so that only the blue color shines. So this is how you can continue to use the traditional 2D compositing for each of these elements after you have converted the deep images into a normal 2D image. Now, let's have a look at where deep compositing really shines, and that is the fog as well as the hair. So over here, I have a grassy background. I have this furry creature that I've recolored, and I have this dense smoke element. Now, first, let's have a look at why the deep pixel compositing technique is not going to be all that much effective. So I have this furry creature over here. If I go to format, I can see that I have already assigned the position paths to the correct channels. And the next thing that I've done is created a volumetric mask, which I can control using this slider. Then over here, I have this blue background. This is just a normal blue background. And I've merged these two together. And I'm going to convert this volume mask into a bitmap and connect it into the mask input of the merge node. And let's scroll in and have a look. So this is what it looks like with the mask on. And if I move the mask around, we can see this is how it's affecting. And the moment we come over here to this tail, we can see we have these edge artifacts, and over here we can see this that it's not able to mask or compute individual hair strands. So this is not a very usable mask. And yet on the other hand, if I go over to the deep image compositing and I have this entire scene, and over here what I've done is I've converted this blue background into a deep image as well, and I'm going to control it using the dTransform node, and I'm going to merge these two together. So this is what it looks like. And if I use the transform tool to move this blue background in the z-axis, we can see over here, not only is it able to compute these hair strands, that deep pixel compositing struggled or basically failed to do so. There you go. And let's bring this over here. We can see this. The DeepToImage is able to compute individual hair strands over here, but it can also do a great job over here when the fur is long. There we go. And let me show you this over here. There, we can see the difference. So this is the power of the DeepToImage compositing, because what it's doing is that it's rendering each of these hair strands as well. And all of this is real time. I mean, I don't have to render it over and over again. This is actually real time. Now, let's also look at the volumetrics or smoke. So let's merge these three together. So let's take this merge node. I'm going to connect this, and the fog like so. Load that into the viewport, and this is what our scene looks like. Now let's add a transform node after the dRecolor node. We're going to move our creature, and the moment I move the creature, I can move the creature in and out of the fog as if it's coming through the fog. This is what I can do with this. Look, it's disappearing inside the fog, and it's now coming out of it. And it is also taking into consideration the fur as well, or the position of each fur strand, and it's accurately able to do so. But yet we can see some artifacts over here. We can see that there are these empty dots, missing pixels, if you want to call it, missing samples. Or if I bring this creature in, we can see these voxel, these square pixels, this huge area. This is another problematic area. And if you look over down here where the fog or the smoke meets the ground, we see this very harsh line where in fact it should be a much nicer, smoother gradients. So we need to understand that this is the initial or the first integration of DeepToImage toolkits into Fusion. So there are bound to be some hiccups. I'm pretty sure they're going to solve these issues with further updates. But right now, let's have a look at how it is actually supposed to look like. So let's go to Nuke. So here we are in Nuke, and this is the exact same scene from Fusion. We have our creature, we have the background, we have the smoke, and we have merged them all together using the dMerge node. And I'll be using the dTransform node to move the creature in and out of the fog. So this is what it looks like at 0 value. And let's bring it out of the fog for now. So press -3. So now our creature is out of the fog, and now let's slowly hide it inside the fog. And with each value change, we can slowly see our character disappearing inside the fog. This is a big jump, so let's try -1.5 or -0.5. And over here, this is what it looks like. 0, 1, 1.5, 2, 2.5, and we can see it's nicely, gradually being interacting with the fog, and we don't even see those artifacts that we saw in Fusion. This is what it's supposed to look like. Even down here where the fog interacts, or where the fog intersects the ground, we can see that there's a nice gradual fade off, that even the grass are being affected. We can see that this grass blade that these grass blades over there are inside the fog, and these grass blades over here are outside the fog. We can literally see them moving inside the fog, disappearing inside the fog. So this is the power of deep image compositing. And that's it for today. I hope this explains what deep image compositing is and what are the tools that are now available to us in Fusion. And now that you have a basic knowledge about deep image compositing, you can apply it in any compositing software that does deep image compositing. So please don't forget to like, subscribe and ring that bell icon. Until next time, see you.